My name is Mark Russinovich. For those of you that haven't seen me present before, I'm the Chief Technology Officer of Azure, so I lead technical strategy and architecture for the Azure platform. By the way, happy 10th anniversary, 10th birthday, Azure. I'm referring to the fact that Azure commercially launched on February 1st of 2010. I joined Azure in July of that year, so I've been there almost as long. And one of the areas that I focus on is our strategy when it comes to containers and serverless and Kubernetes and Service Fabric and what we're going to do in that whole space. And what I'm going to share with you this afternoon is a view into the direction that we're taking things. I want to preface this by saying that in this space, which is very fluid, there's lots of people contributing, lots of innovation going on, that there's no sure thing that what I'm going to show you is the thing. What I do believe is that it solves a lot of the problems that we've identified in Azure and Microsoft when it comes to wanting to be serverless, recognizing the fact that Kubernetes has really taken over when it comes to infrastructure, especially infrastructures that we don't operate, out on the edge, for example, where customers are deploying Kubernetes or in their own data centers in a hybrid scenario. And so what I'm going to talk about are the problems that we've recognized inside for both first parties that want to go serverless, but also want to go to edge, as well as what we've learned from third parties that are also adopting Kubernetes and containers and microservices. And that is boiled up into the strategy that I'm going to share with you today. How many of you have played with Kubernetes, just out of curiosity, just get a feel for the technical kind of background of the audience? And I want to say that you don't have to have background in Kubernetes to understand what I'm going to share with you today. What I'm going to share with you today are the concepts. I'm going to get somewhat into technical details. So those of you that are staying up at strategy level, I'm going to get a little bit technical. I'm not going to get down into the weeds of the detailed architectures behind these things, because we just simply don't have time in an hour. First things first, though, we need to have some definitions. And I found that in this space, lots of people refer to app models and programming models, and they mean different things from each other. And so one of the things that we wanted to establish right up front was, when we call these things, let's all have the common understanding of what we're saying and what we're referring to. So this is an attempt to define terminology at Microsoft and hopefully for the industry, starting with an app model. So what is an app model? An app model is the way you describe a deployment or collection of components that you want to deploy and you want to manage the lifecycle for. If you're just talking about a single function, that's not an app model. If you're talking about a function with a front end that is containers that are load balanced and you just want to describe that as my app, you want an app model that describes the relationship between those things. And enough detail that you can hand that to an infrastructure and it knows how to wire those things up, how they depend on each other, how they communicate with each other, what kind of security boundaries they've got. And so that is what we're talking about when we talk about app model. It doesn't have anything to do with the code that's inside those components. It doesn't even mean they're containerized. It just means this is the way to describe these pieces and how they fit together. On the other hand, a programming model, programming kind of gives you the hint that it is for the programmer. It's for a developer. It's the interfaces, the abstractions, the APIs that a developer uses, frameworks in their code to talk to other services that are their own services that they're talking to in a distributed architecture, or external services, like a PaaS endpoint or another applications endpoint. But it's really requiring the developer to buy into some aspect of the model and adjust their code accordingly. App model, no developer. In fact, you can think of app model as more of an operations kind of IT thing, packaging it up, developers involved with describing, or an architect. But developer or program model, that is when you're talking about actual code. So with that behind us, introduce the application model that we've developed and the programming model we've developed, programming model runtime or platform, really. So open application model is a specification. It's not an actual implementation, concrete implementation. It is describing, here's the schema for how you describe the architecture of your app and the pieces and how they relate to each other. Dapr, on the other hand, is a distributed application runtime. And you'll see why I call it a runtime or a platform, because it's non-prescriptive and you can really do lots of different things with it, including buy wholeheartedly into it and just, you're in a Dapr app, or you can just use bits and pieces of its functionality. And I think that's one of the things that makes it so powerful. So I'm going to spend some time talking about the background of these things, and then I'll get right into Ohm and implementations of Ohm. So these actually came from, like I said, us looking at first and third-party requirements. Early last year, late the year before, as we looked at all these requirements, we had the realization that there was opportunities here, there was white space out there. Nobody had gone and addressed these kinds of problems with anything. And so this is an opportunity for Microsoft to lead, but the new Microsoft can't just say, here's the thing, everybody, and it's a Microsoft thing. This is the Microsoft distributed runtime. In the new world we live in, it's open. We've got customers that are saying, I only want to buy into things that are truly open and vendor neutral and work on any cloud and work on any edge or hybrid environment. And for that, we have to embrace the true philosophy of open source. So we launched these as open source projects in November. So we made announcements about a few weeks before Ignite, and then we talked about them at Ignite. How many people saw anything about Ohm and Dapr from Ignite? Just out of curiosity? OK, so just a few of you. But the idea is that we're building communities, and we're getting other people to contribute. We want partners. And so we're looking for partners that we can work with to develop these things. And eventually, they'll go into open source consortiums. The reception has been pretty incredible, especially to Dapr, but also very strong to Ohm. Ohm is one that's harder to understand the need for, but Dapr people get. And just to show you kind of concretely, one of the ways that people measure how much does the open source ecosystem like something is with GitHub Stars, where you can go to a project and star it. And if you take a look, we've got a graph here over, this is 180 days, so 6 months period. The blue line at the top, that's Dapr Stars. Dapr's just passed open source projects like Linkerd, but the one that is in orange is a good kind of comparison for something that's hot. That's Kubernetes, GitHub Stars, up to 6 months. And so you can see at 3 months, Dapr's already passed Kubernetes. Now the Ohm lines, there you can see one of the Ohm lines is that dark blue line. So if you look just under the orange line, there's the Ohm line. It's flatter than Dapr, but we're just getting started with that, and we think we can raise that up. But you can see the other open source projects that are in that comparable space, it's already doing better than those. So really good traction right off the bat. So Ohm, let's talk about Ohm. And by the way, you can just go to ohm.dev as the entry point for Ohm. But to understand how we were looking at the requirements for Ohm, one of the things we realized is, like I said, the cloud is going serverless. Customers are coming to us and saying, I don't want to manage any infrastructure. I just want my devs just to be able to write their apps and deploy them, and the right thing happens, and my infrastructure operators don't have to do it. That's your job. Make it easy for me just to run my business. On the other hand, if you take a look at what's going on at the edge, it's Kubernetes. And the fact is, a developer that wants to deploy something to Kubernetes on the edge, they have to learn Kubernetes. They've got to describe their app in a Kubernetes manifest and learn the YAML and the components that make up a Kubernetes app. And the fact is that Kubernetes has gotten mind-bogglingly complex. It's got so many bells and whistles on it at this point that it's just a little bit overwhelming. But not only that, if you take a look at what Kubernetes really is, it's infrastructure. In fact, you go listen to Google talk about it, they'll say Kubernetes is infrastructure. It's not an app platform. It's really to operate containers and orchestration of containers. It has no opinion about describing really apps. So if you take a look, one of the things that people are using, they're using Helm to describe their apps in Kubernetes. And that's one way to parameterize their Kubernetes manifests and deploy them and kind of get some aspect of app, but it's still incredibly complicated. I was talking to the CTO of Walmart about 2 months ago, and he gave me a line that I think really we're starting to hear from enterprises. Developers don't let developers near Kubernetes. And that's simply because it's so complicated. At Walmart, just like other companies we talk to, they're building abstractions on top for the devs. And if you take a look at what devs we're talking about here addressing for Microsoft, it's enterprise devs. The people that are writing apps right now and directly writing Kubernetes manifests aren't your standard enterprise devs. They are your, I'm really hardcore into technology, and I want to learn everything, and I want to be the best and be on the cutting edge. Enterprise devs, they've been doing .NET and Java, web plus database, basically, type apps, and they just want to get their job done. And saying, oh, to get your job done, go learn about Kubernetes and CRDs and everything else that goes goes with Kubernetes, you've got a problem. All right, we're back. Somebody got really excited about Ohm. I hope they're okay, because it's getting more exciting from here. So let me talk about the problems that Ohm is addressing. One of them is that when you talk about Kubernetes, and you want to talk about moving from cloud to edge, is Kubernetes isn't app-focused. And so one of the propositions of Ohm is that it lets a developer focus on developer aspects of describing the topology of their application. It also supports a separation of concerns. So not only can developer do what they want, but it gives the infrastructure operator and the application operator, personas that I'll just introduce in a minute, the ability to do their jobs and map applications onto their specific infrastructures. Every Kubernetes cluster is different, for example, and a serverless infrastructure is different than a Kubernetes infrastructure. And then finally, it's designed to support both cloud and edge, including, and what that means is serverless in the cloud, Kubernetes, and even other infrastructures that might show up for edge computing, including tiny computing devices, support that as well, so abstracted from the infrastructure. Now let's take a little bit more look at these. One of them, the first value proposition, that it's application-focused, is that it supports modeling of the application in a sophisticated way, so non-trivial applications, and lets a developer specify all of the concerns required for infrastructure to understand how to lay out and connect their application and the pieces of it, the microservice parts of it. I want to just point out that I'm talking about microservice-based apps, but this doesn't just apply to a microservice-based app. It can be a monolith with just a couple tiers in it, but it gives you this value proposition across the spectrum of the complexity of those applications enterprises are going to be developing. So things like ingress controllers, load balancers, autoscalers, all of that is describable in this model, both abstractly from a developer's perspective, and then concretely from an infrastructure operator's perspective. By separation of concerns, there's three personas. One of them is the developer or architect. We're just going to call those as one combined role, the developer, that writes the code for the app, packages it up, figures out the topology. This front end is going to be load balanced and talk to this back end, and then hands that off to an application operator. The application operator is responsible for taking that app definition and deploying an instance of it. And they might deploy multiple instances if they've got different environments, for example. I want to take this app, and I want to deploy it in the cloud. I want to take the same app. I want to go deploy a version of it on-prem. I've got a super sensitive version of this app, instance of this app. It needs to be air-gapped. I want to be able to go do that. So the app has to be parameterized in such a way that the application operator has the controls necessary to customize it for the particular environment, where the developer has the ability to specify what constraints within which to customize it. And then finally, the infrastructure operator, that's the person that's running the Kubernetes cluster. That's the person that today is, a lot of times, authoring these Kubernetes manifests or working with the app teams to author them to deploy them onto Kubernetes. Because they're the ones that say, you know what, in my Kubernetes cluster or my infrastructure, I'm using Kata as the autoscaler. In another one, they'll say, I'm using Istio as my service mesh. And there's different versions of each of those components, and different infrastructures will have different ones. And so what they will do is they'll take the application and say, if somebody's using autoscaler, they're going to use Kata. It binds to Kata. Or in some cases, they'll say, I've got two autoscalers. Developer can pick, or the application operator can pick, rather, which one they want. And then the cloud and edge aspect. That simply means that we're designing it so that it is highly portable down to even small class devices like Raspberry Pis. Anything that can run Kubernetes for sure, because Kubernetes is a target, but we want to go even smaller than that. Describe anything wherever it happens to land, including even an Azure sphere. So this is putting it all together. The application developer has got the code and containers. They describe that as an application in their topology, hand that off to the application operator, which then says, hey, I want to do traffic management. I've got security, identity that I want to map into this application, and then deploying that to the infrastructure, described as an OM collection of manifests, and then that goes onto Kubernetes or serverless infrastructure. And that is the full stack right here. So let's talk a little about the pieces of the app model. Just more concretely, I'm going to move somewhat fast through this, just so you get a flavor for the different pieces that are showing up to support the richness of complex applications, starting with what the application developer architect would describe pieces of their app as components. And this is one of those, like, everybody argues over which word to use: component, microservice, service. We've settled on component. Want to make this look Kubernetes friendly, so that's also one of the reasons. But you can see a workload type. And a workload type can be, it's a scale out component, or it's a singleton component. It doesn't scale out. That's just one example, simple example of a type. Everything's parameterizable. The application consists of putting these things together and then also specifying the relationships between them through things like application scopes that I'll describe in a second. Now, the application needs to be bound to an infrastructure. So an instance gets targeted at a particular infrastructure. That's where the infrastructure operator has defined what are called traits. And a type of trait would be an autoscaling trait. And you could have multiple instances, like I mentioned, a manual autoscaler, a CADA autoscaler. Both of those would be traits, and so the application operator, if there's a choice, gets to pick which trait they want to bind the application to. There might not be a choice in some cases, in which case they just get the default trait that the infrastructure specified. You put all this together, and what you've got is an answer to how do I create an app where the developers don't have to learn Kubernetes, yet where the infrastructure operators get control over the way the app behaves, and it can go from cloud to edge, and it can go to serverless infrastructure, like a platform in the cloud where you just hand your own app with the configuration, and it doesn't matter if it's Kubernetes underneath, it's just going to work. That's the vision. So a little bit deeper into each of these components. There's just an example here. I'm going to just slide through these. These are kind of reference slides for you to just when you get the deck, because I'm going to show you a real example. I'll stop here, though, on application scopes, which I didn't describe up front. A scope is a way to loosely couple a bunch of components. And the reason you would want to do that, there's one example there on the slide, is a health scope. The idea is that this is extensible, and so everything in OM is extensible. So we can describe a health scope, and that health scope you can see specified over here is a way to say all of these components together, there's some metrics that come out of that boil up as a health metric. This thing is healthy or unhealthy. This part of my app, this whole section of my app is healthy or unhealthy, which is important for an application operator to know. But it's the developer that knows, hey, this stuff right here is all related, and so that stuff needs to be put in the scope so that somebody that's operating my app knows when this thing exceeds these kinds of thresholds, it's moved into unhealthy territory. So another example of using scopes is the network scope. And the network scope would be something for security, where I want these parts, these components of the app to be able to talk to each other, but shouldn't be able to, the front end shouldn't be able to talk directly to the back end, for example. And so I can isolate my app into different network scopes without having to get really into the prescriptiveness of, hey, there's a VNet and a subnet, and these things should be in this particular subnet. The application developer, at the time they develop the app, who knows what VNet or subnets they're going to go into? They just want to specify the logical constraint. These things need to be able to talk to each other on the network, and so that's an example of a scope. And then finally, the application. You can see an application manifest there, which has a front end and a back end. They just simply reference the components. Now that they've referenced the components into this application manifest, they can hand that off. And then the final step would be for that to be bound on the infrastructure. Here's a trait for a manual autoscaler and a trait for an ingress controller. You can see there. This would be in the Kubernetes infrastructure. And then finally, the application configuration. The application operators taking anything that was parameterized and any trait where there was a choice, and then binding the app, effectively making a real instance for a particular purpose. Now, that is the spec. And the spec is open. So the spec is abstract from any implementation. Of course, one of the most important, if not the most important implementation, is for Kubernetes. If I've got an Ohm collection of manifests, how does that deploy to Kubernetes? And the answer is a project called rudr. That's why we launched them both at the same time. Here's the spec. Here's the Kubernetes implementation. And anybody can come up with a different implementation. And I'll talk about somebody that's working on another implementation. But rudr uses Kubernetes primitives, custom resource definitions, or CRDs, to be able to model these things and get the right behaviors out of Kubernetes to bind, for example, those components to their traits underneath. And that is something that rudr then will be our story for taking apps that we develop ourselves or that customers develop ourselves out to edge devices. So one part of our strategy, which probably has already come through, is that Kubernetes is the infrastructure out on the edge. When it's not under our direct control, we have to use Kubernetes because customers are betting, the ecosystem is bet on Kubernetes, and they want to take advantage of that. And then, so you use rudr, deploy your app to Kubernetes, and you end up with pods on Kubernetes, wired up in the right way, bound to the ingress controllers and autoscalers, the way that you specified, all the way up in the application model and the configuration. So let's take a look at a real demo of a fairly simple app, just to show you the concepts here of a front-end and back-end app, just to show you two things. One of them, that I've got separation of concerns in play. Second is that it's highly portable. Now, the code of this app, this back-end and front-end, it's a web front-end, and it's a back-end that's moving around objects that we're going to see in a web front-end. That is something that is portable code. It's in containers, and I've got here a component schematic, which is the application manifest. Here's the workload type for one of the components, a singleton server, which means it's not auto-scaled, and that's just for simplicity. We just got it scaled to 1. It's parameterized, and there's a parameter called ohm texture. It's a string. It's required. The default is texture.jpg. And then I've got a container that's part of this workload, the front end. And here's the image for that front end. It has environment variables that it wants Ohm to define for it. An environment variable called texture, which is going to get its value from texture.jpg. And that is populated from that Ohm texture that I saw above. So this is a way that a parameter comes into the app and into the component. And then you can see I've wired ports on an ingress controller. And then the back end, very simple back end, singleton server, back end. Here's the container image. Here's what it's going to be listening on. So I've just described a front end and back end that's parameterized. The front end gets a parameter, which is some texture. We're going to see what that texture is for in a second. In fact, right here, I've got a configuration file. This is the application operator's configuration file for deploying this application to AKS, Azure Kubernetes Service. And you can see that in this application, I've only had to specify a couple things. One of them is the Ohm texture, and the value is AKS. So the app is going to be looking at this texture environment variable. If it sees AKS, it's going to pull the right texture for a deployment to AKS. And then the second thing is this ingress controller, where I've said, when I deploy this app, I want the ingress controller to have a host name, a DNS name, of aks.azurecto.com. And then the back end, the only thing I had to specify there is the back end's name. So let's go deploy that. And I'm deploying using standard Kubernetes APIs. There's the application manifest, and then there's the config. And I've just deployed that. Now, what's going to happen, that's going to deploy here in a second. Let me deploy to two other infrastructures at the same time and show you the configurations files for those. Because we're going to take that same app. The only thing we've changed is the configuration manifest for the Ohm application. And the way that we've configured it is this time we've said change the texture to EKS, change the endpoint to EKS. And that's because what I've just done is pointed at Elastic Kubernetes Service, AWS's version of AKS, and then deployed to that. I'm also, just to show that it works on the edge, deploying the same thing to these Raspberry Pis up here. So the front and the back end are being deployed onto this. There's a Kubernetes cluster on that. These 3 Raspberry Pis here, or it's actually 5. And the only thing I've changed here is the texture, but otherwise the commands are the same. So let's go take a look and refresh. And you can see AKS. Well, I specified the AKS logo. Texture, EKS, there's the EKS logo, and Raspberry Pi, there's the Pi logo. Same app, containerized, same images except for the Pi. They were the ARM images instead of the x64 images. But I've now, I think, demonstrated for you this whole value proposition of Ohm. And rudr is the implementation, which is the developer didn't have to know anything about Kubernetes. They were able to describe their app, parameterize it, application operators be able to customize it for their particular infrastructure, and it's portable across all 3 of them. Now, what we expect is that even enterprise developers don't like writing YAML files typically, so Visual Studio Code will be letting them specify, project with front end, back end, here's the relationships between them, and spit out these kinds of manifests for them. Really, it's about aiming for this coming wave of enterprise devs that are being asked to develop, hey, build me a resilient cloud scale application that doesn't fail when you really need it not to fail in front of the whole United States. So if you take a look at what else is going on in this, and that was a election joke. Really? Nobody really watched what happened the other night? Yeah, OK, Iowa. Yeah, Iowa caucus app failure. If you take a look at what else is going on in this space, we're working closely with Alibaba. Alibaba totally bought in. Their developers inside in their infrastructure, they're building a lot of their infrastructure on Kubernetes. And what they found is their own devs are like, Kubernetes is too complicated. These are not even enterprise devs. These are cloud devs. And they're like, we don't want to worry about Kubernetes. So they're building a managed version of Ohm themselves called an Enterprise Distributed Application Service, which is the Ohm model where you can take that same manifest, hand it to them, and it'll just work. And it's all completely managed underneath the hood, serverless. You don't know it's Kubernetes. It's all just abstracted away. And so a great example of a company that's bought in fully already seeing the signals from them own devs as well as their customers. So that's Ohm. Let's switch over to Dapr now. And you might have heard of Dapr. This is the T-shirt, the logo for Dapr. Dapr's really excited people. And I'll say why it's excited developers. Ohm is one of those things that's like, OK, it's not really that exciting. It's kind of like infrastructure. You need it, but it's not going to really revolutionize anything. That said, it does solve real problems. Dapr really kind of is a disruption, I believe, in cloud-native programming models. Let me introduce the problems that enterprise developers are facing as they're going into this cloud-native world. One is that, like I just mentioned, they're being asked to create these distributed, resilient apps. Zero downtime. No more of the bank is down for an hour while we upgrade. It just needs to upgrade seamlessly. They write in many, many languages. Like, there's always the state of languages, and there's like this 10 like main languages people use, and then there's another long tail of another 10 to 20, and there's a new one showing up. Like Rust just showed up on the scene. It's like taking the world by storm. And what the problem is that when they look at adopting something, they're saying, I want to adopt this thing, but I want to use my programming language. And they also want to leverage existing code. So much existing code out there that they just want to use as libraries. Or their companies have built their own pieces of apps and code that they say, you will use this for this particular task. And so they've got to bring that in. So if you say to them, hey, here's a new programming model. By the way, Scala is the language. You got to do everything in Scala. And by the way, it doesn't really integrate with anything else. Everything from scratch has to be written in Scala. That is doomed to failure. You're going to get some Scala hardcore people adopting it, but not much else. And then finally, when we take a look at programming models, like what really makes people's lives easier with creating a distributed app, which enterprise devs are being asked to do? One is functions as a service, which Lambda introduced and which has taken the world by storm, and we've got Azure Functions in our space for that with its own innovations that influenced Dapr. But enterprise dev can sit and write an event-driven, microservice-based app that's highly scalable, highly resilient, and just deploy it and not worry about infrastructure using Azure Functions or using functions as a service. So really powerful for enterprise devs, really right up their sweet spot of I don't have to become a distributed systems expert to use this thing and be productive. The second one is virtual actor model. So a virtual actor model you can think of as kind of stateful functions. Functions are stateless. They don't store anything. That's how they can scale out so easily. But an actor is, you can think of it as object-oriented microservice. There's a class definition. There's some interfaces or methods on that class. And then you instantiate instances of it, giving them each an ID. And each instance has its own state, like its own class variables that it's, or object variables that it's defined, populated. And so when you want to talk to instance 5, you want to know what instance 5's state is. Instance 5 is running. Instance 5 is stopped. Instance 5 has a color blue set on it, or a color red, or a temperature 65 on it versus 63. You get where I'm going with this. It is also something that is really powerful tool for enterprise devs because they don't have to worry about distributed programming. Actor model you just reference by its ID, and the system goes and finds it and routes your message to it. They don't have to worry about managing the lifecycle of these things. They don't have to say, let me go create 5, oh, and let me go shut down 5, because the virtual actor model simply says, hey, once you reference 5, we'll create it for you automatically. And you know what? We'll get it running on a computer if you need it. If you don't need it, we'll shut it down. We'll hydrate it or dehydrate it. We'll whatever, we'll freeze it, and then we'll bring it back if you call it again. And all that stuff you don't have to worry about. So really powerful for enterprise devs. The problem is, when you take a look, one of these problems in these models is that they're not incrementally adoptable. If you take a look at some of these functions as a service, really you're bought in to functions as a service. Really hard to bring in other code, types of code into it. Second is that all these models, they're specific to different languages. If you take a look at akka, which is one of the actor model frameworks, it supports Scala, and then a separate effort supports .NET on it, so C# and F#. But if you want to do akka-type actors in Go, which is really powerful, popular cloud-native programming, you're out of luck. And same thing with Azure Functions. It took Azure Functions until now to get Python support, even though Python's always been one of the top 5 most popular programming languages in the world for the last decade or so. It took a long time to get that into Azure Functions. And if you want to do Azure Functions in Rust, you can't, because it doesn't have that Rust integration yet. So Dapr is aiming at addressing these problems, having a sidecar architecture, supporting cloud and edge, and then having a collection of building blocks. And let's talk a little bit about each one of these and what they give you. One, the sidecar architecture means that you don't have to import an SDK into your code. The sidecar architecture is implemented by having all of Dapr's functionality being exposed to the app through an HTTP or gRPC endpoint. And that means you can simply, from your app, call it like a web service. You don't have to import the Dapr SDK to talk to it. You just pass in JSON or gRPC form payloads, and you're now talking to Dapr from any language, including Rust, right off the bat. Supports Rust. If there's a new language called, make up your language name, tomorrow, it will work with Dapr. So no need to wait for a language integration. It comes in 2 forms. One is, we don't think the whole world is necessarily going to move to containers. When you get down to small IoT devices, you're not going to have the support, the amount of resources necessary to support Docker containers. So there's 2 forms that you can use Dapr. One, and also of an existing code that's non-containerized, you can just use it as a process-based model, where you load it up and you talk to it from one process to another. We call that Dapr self-hosted. And then there's Dapr Kubernetes hosted, where you actually deploy Dapr under a Kubernetes cluster, and it manages all the setting up of the distributed state in that Kubernetes cluster for you. And also, when you deploy a pod that is your application code with annotations in Kubernetes manifest, Dapr sees those and injects its sidecar, its little proxy agent that talks to other Dapr services. So really lightweight and easy to just bring in to existing code. Now, as far as cloud and edge, again, the idea is that Dapr is extremely lightweight. It says nothing about what infrastructure you deploy it to. So I've talked about Kubernetes. You can deploy it to Kubernetes. You can also deploy it in your ASP.NET website. In fact, we're working closely with the ASP.NET team to have ASP.NET integrate with Dapr to take advantage of some of the capabilities of Dapr. So wherever you've got ASP.NET, you can put Dapr and start to use Dapr services. That means that you can take it down to the edge, Kubernetes on the edge, or even smaller devices on the edge that don't support Kubernetes. And the last one, microservice building blocks. This is one of those, you don't have to suck in the whole thing. You can use it bit by bit. And you can see all of the services that Dapr provides you out of the box here. As a developer, you can take advantage of one of them, 5 of them, or all of them. It's up to you for what value you want to get out of Dapr. So I think this is what's so exciting about it is if you take a look at all these, today, a developer running a distributed cloud-native app has to cobble all this stuff together. We call this kind of best practices as a service because these building blocks represent best practices for distributed programming. If I want to call an API, if I want to call one microservice to another, that's service-to-service invocation over there on the left, today I have to worry about, first I have to do service discovery, then I've got to call, then I've got to worry about errors and do retries and backoffs for throttling. That is built into Dapr. For Dapr, I just call one of my microservices A, I call the other one B. If B wants to call A, it just says to Dapr, hey, send this stuff to B, or sorry, to A. Dapr takes care of finding out where A is. Dapr is responsible for getting the message to A, and it does retries and backoffs if there's errors, kind of following best practices. And so the developer just didn't have to worry about any of that stuff. So let's take a little bit deeper look at each one of these, starting with state management, which is I want to be able to store some state. Now, what I typically would have to do is load up an SDK for some key value store, learn that key value store's idiosyncrasies, and then call those APIs, set up the connection, call it, backoffs, retries, all those things. Or my app now is loaded up with 20 different SDKs for all the components it's using. With Dapr, you've got state bindings where people can plug in state stores, and now if you're a Dapr app, if you want to use state, you just write a JSON payload to Dapr state, and Dapr takes care of it. And you can bind it to whatever state store you want. There's about a dozen now different state stores, Cosmos DB, Azure Tables, SQL, are examples of state stores that you can put on, integrate into your Dapr environment. Bindings are another example. I want to send some output out to some other service. That's called a binding. This is inspired from Azure Functions. Developer, again, don't worry about connection strings, connection management, retries, backoffs. I just talk to a binding, and I reference the binding by name. And now I've got best practice implemented over there, including key management and all those other problems. The developer just called that API in Dapr and took advantage of the ecosystem's implementation there. By the way, the Twilio one at the bottom, does anybody know what Twilio is? It's an API. It's an API as a service. It's for text messaging. It's the primary API. And the reason I'm highlighting that one is the best binding on that list. It's the best binding because I wrote it a few days ago. And I just want to highlight, because I sat down, I'm like, I'm going to write a binding for Dapr Twilio SMS is missing, and I've written microservice-based apps that use SMS. It took me an hour to write it. And I'm pretty new to Go, so it's written in Go. Despite that, it took about an hour, and it ran on the very first time. And now it's checked into and approved as part of the Dapr contributed components repo. So now anybody can take advantage of Twilio SMS in Dapr apps. So let's take a quick look at a demo of this. And I've got a little simple Python program that calculates pi. And when I run this thing, this app, you can see that it's got 500 iterations. I'm going to calculate for 500 iterations pi. But if I terminate it, I just stopped at 270. And every time I run it, it starts from the beginning. But if this was a real app and I wanted to make it resilient, what I want to do is make it so that it can remember where it was. So with Dapr, here I get the Dapr local endpoint using the OS environment. And I've got two functions that I've written, getState and saveState. So if we take a look at saveState, it's creating a JSON payload with all of the state that the calculation uses, and then posting that to Dapr State Store. That Dapr State Store I actually have in a Redis database. This is the Redis configuration for Dapr that says, hey, here's the Redis database to store that in. But the developer didn't have to clutter their code with all that. They just call into Dapr. Here's the JSON content. And then you can see when it call getState, it just calls into Dapr, and it says, give me the state. So if I go and uncomment getState and saveState, so here's getState, where it's going to pick up where it left off. And there's the saveState after every iteration. And now I run this again, but I run it with the Dapr runtime. And Dapr runtime starting up. Now let me terminate. And you see that I got to 69. Let's run it again. And if I scroll up, you can see it picked up right where it left off. And so that was no changes to the code at all. And there it printed out pi. Now the thing is, with just a couple lines of code, the post standard stuff that any enterprise web developer knows how to do, talk to HTTP and use JSON, I've just made this app resilient. It now can tolerate failures and pick up where it started. I also want to save the output to a state store. And so for that, I'm going to go back to the code. I'm going to save the pi calculation. So I'm going to save that in a state store. In the state store, here's the configuration for that. It's Cosmos DB. I could switch this out and make it DynamoDB. The code is going to not be changed because this is basically JSON payload that I'm dumping in, and the binding takes care, the state store binding takes care of everything for me. The connection string, the authentication you can see right there, the retries, the backoffs, all that's implemented in code behind this. And as a developer, I just had to say, I just had to put together the payload and say store pi, and then call into Dapr and do it. So let's run it again. And it's going to start where it finished and just write pi out. And if you take a look, here's my Cosmos DB database, and it's already written it, and there's pi. And now that is it for what a developer had to write. So really powerful way to get some functionality. And you can see this example of I've just adopted some Dapr functionality. I want to do bindings for my output. I want to do state store to record results and be resilient. Few lines of code. The rest of it taken care of by the bindings itself, and all I had to do is provide some little bits of configuration. Imagine a developer sitting down and you saying, go, hey, by the way, use Redis to save your intermediate state. Use Cosmos DB as the output. So they'll go and import Cosmos DB and Redis SDKs, implement that functionality, and then you come back and say, you know what? Instead of Redis use DynamoDB. And what they now have to go back and do is import that SDK and have another version of the code. In this case, because that's abstracted, the exact same code will work across different environments. And then do you get these emails from your family members? Right as I was coming to this talk, my mom sends me an email. Hi, what happened with that app in Iowa? Love, Mom. Like I'm the expert on the app in Iowa. So what I wrote back is the app doesn't save the count when it terminates if they'd only use Dapr. And she said, oh, yeah, of course. Let me talk a little about service invocation. That is what I mentioned before, is I want to do service-to-service invocations, not just some external thing. Really simple in Dapr. I've got names from front end and cart for my different microservices. The cart has a method called checkout, and when the front end calls that with a payload to say, hey, cart, I'm checking out, here's what I'm checking out with, that goes into Dapr's endpoint. Dapr says, here's checkout, and it does a post over on the remote side. Again, developer didn't have to know where checkout was. In fact, this is one of the powerful things about Dapr in this approach, is that checkout can be on-prem in the store, and cart can be up in the cloud. Or it could be together. The developer doesn't have to worry about it. Their code is going to work the same regardless of the topology. In fact, the same code just can be packaged in different ways and continue to work in this distributed way. One of the other capabilities is triggers. How do I get some input into Dapr? And Dapr's got a bunch of input triggers. Let's say that something shows up in a Kafka feed. I want my piece of code to respond to that. This is event-driven programming. And this can be stateful event-driven or stateless being functions as a service. And you can see the kinds of triggers that have already been written for Dapr. So you can say, if something shows up in this Redis database with this particular match, invoke me. And then I can take a response. And so Dapr sitting there with its bindings, developer doesn't have to worry about anything except for registering, hey, I'm registered here on this trigger. The configuration says the trigger is based off of Redis. And the developer code is extremely minimal. All the heavy lifting is done in binding. PubSub is another example. I don't want to do direct service-to-service invocation, but I want to do some messaging between my services. Or I want to do messaging from my service to another service. So I'm going to use PubSub. Either I'm subscribing to messages or publishing them. Again, with PubSub plugins in Dapr, and there's a whole bunch of these. Here's Redis is just one of them. I can have two subscribers here to learning about order, where both these microservices need to respond to an order coming in, but all they had to do was say, subscribe, no Kafka, no Redis code. They didn't have to import any of that. They didn't have to do retries. They didn't have to do authentication. All of that was handled by the binding in the configuration of the binding. Again, very trivial. And then a big one. How do I know how my distributed app is working? There's a lot of different tracing mechanisms out there. And developers have to pick one, have to instrument their code, have to configure the tracing mechanism, to upload, and all of the other things they would have to do. Wouldn't it be great if the developer basically didn't have to worry about any of that? Only at the time of deployment do you specify, you know what, for this instance, I want to use App Insights, or I want to use Datadog, or Instana. Anything that's conformant with Open Census, there's a plugin for Dapr you can take advantage of right today. So I want to show you a quick demo of kind of a gratuitous distributed microservice app. This is my favorite Dapr demo, because it's kind of ridiculous. But imagine that you're a developer, you were told, here's the deal. You're going to write a calculator app. It's going to be a React front end. So we were all bought into React. It's going to have nice buttons on it. When the user clicks on plus, you want to call the plus microservice, which is going to be somewhere in your Kubernetes cluster or somewhere in your infrastructure. And it will return to you the results of the plus. When you call multiply, have a multiply microservice. Divide, have a divide microservice. You get the idea. We also want modulo, too, by the way. That's really going to throw a wrench into things. And I want this app to serialize its state. I want it to remember the state of the calculation as well. So if it terminates, I want to be able to restart it. Oh, and by the way, this thing needs to be portable between AWS and Azure. So go make all that happen. Oh, and I want to know how this thing performs. What's the slowest microservice? So that is what the developer has in front of them. Now imagine standard workflow today, sitting down as a developer with your customer and saying, you're going to build this. How are you going to build it to accomplish all these things? And you're probably thinking about hundreds, thousands of lines of code. And that's really what it would be today before Dapr. With Dapr, I can take advantage of bindings. I can take advantage of service discovery and service invocation to make this thing trivial. And literally, I haven't counted the lines of code, but you'll see the full app. I'm going to show you every single line of this app, and it's probably like 200 lines of code. And it's resilient. It's portable. It does everything we just asked it to do. And, oh, by the way, I forgot to mention, the languages that we've got here, you know, the dev team that does the multiplier, they want to use C#. The dev, or the adder. Basically, we've got different dev teams writing each one of these microservices. One wants to use Python. One wants to use JavaScript. One wants to use C#. One wants to use Fortran. See. We'll see. All right, so here's this app. I've got the React server. And the React server, when a multiply button's called, it just posts to Dapr at the multiply endpoint. There's the Dapr URL. Call method multiply at the multiply app. Same thing with divide. Same thing with modulo. Now let's go take a look. This is the whole React controller right here. That's it. Here's the adder. The adder is written in Go. And here's the whole thing. That's it. It's listening to add. On port 6000, when an add method is called, here it is, takes the operands, adds them together, returns a JSON payload. That's it. Here's the subtractor. This person, this team wanted to do it in C#. Here's the C#. That's it, the whole thing. Here's the multiplier. They wanted to do it in Python with Flask. That's the whole thing. Multiplying two things, returning it. Here's the divider. This one's written in JavaScript. Oh, and I wasn't kidding about Fortran. Here's the modulo operator. I thought it was appropriate. Modulo, not F90. And then you can see it's a little bit longer than the other ones. OK, so let's go and run this. I'm going to deploy it. And I'm deploying it to a Kubernetes cluster, AKS. And I'm going to show you that it's actually a full distributed app with different pods. You can see there's the Dapr components. Here's the divider pod. Here's the modulo pod, the multiplier, the subtract, and the adder. There's the whole thing sitting on my Kubernetes cluster. Let's get the IP address. And by the way, I'm going to run a little bit over because of that pause that we had there in the middle of the deck presentation. So I'm going to run over about 5 to 10 minutes. That's OK, just to make sure I get through everything. And there's the IP address. And what I've got open here, this will take a second for this IP address to be lit up by the Azure SDN stack. But I've got the network trace view, so we can see the HTTP commands coming out of the Dapr, the React front end. This will just take a second to come up. So let's do a refresh. It's coming. Yeah, it's the Fortran slowing everything down. It's running on a mainframe. And come on. This isn't Dapr, by the way. This is, oh, maybe I typed in the wrong IP address. Ah, that was the problem. Yeah, there we go. All right. Wrong IP address. That will help getting the right one. So, OK, so watch over on the right side. 9 times set 3. You can see persist, persist, multiply, persist. These are the calls into Dapr. Plus 8 equals modulo 3 equals. And look, it actually worked. Everything calculator worked like you'd expect it to. That's all distributed microservices implementing this calculator. And the cool thing, like I mentioned, is that we got tracing as part of that. I specified that I wanted app insights. You didn't see any reference to tracing anywhere in that code, but I've got a full app insights log of everything that happened in that Dapr app here. Not only that, but I can take advantage of applications insights app map functionality. And there's the whole thing. And this is kind of cool because I can see which one is the slow one. And in fact, if we take a look at the modulo one, 1 millisecond. If we take a look at, let's see, subtract, I can't remember what languages these were, divide, 1.1, 1. Oh, an outlier here, 2.7. Anybody know what language, guess what language this one's written in? Python, yeah. So this one's Python, and I won't make any comments about that. So let's go back. And I mentioned some of those programming models that really make it easy for enterprise devs to write distributed apps. And I've shown you some building blocks. But let's talk about functions as a service and its relationship to Dapr. Because if I want to write a stateless event-driven programming, I'd like to use a functions as a service, triggers, fire my thing, it auto-scales out. I want to do that using Dapr. And the thing is, I can use it in Dapr. In fact, what I'm going to show you is that with Dapr, because it's incrementally adoptable, on top of these microservice building blocks, I can take other functions as a service runtimes and put them on Dapr. And once they're on Dapr, they can take advantage of all the bindings that Dapr has. So I'm going to show you that in action right now with functions on Dapr. So what I've got here are 3 functions apps. Now, this one, you might see that it's not an Azure functions app. This one's a Lambda. So AWS has taken their runtime and made it so you can deploy it outside of AWS. So what we've done is taken the AWS runtime and put it on top of Dapr. One of the triggers that's missing from Lambda is Kafka. What I've got here is an app that I want functions to fire when a Kafka event triggers. And I want that to then result in a logic apps execution, where I'm going to tweet the body that comes into that Kafka payload. I can do that using Dapr even on AWS Lambda runtime, where it doesn't know about logic apps, and it doesn't know about Kafka, because I've got logic apps and Kafka bindings with Dapr. And it's as easy for me to sit in my Lambda, and here you can see it's calling into logic apps with the body that it gets from the Lambda handler, which got passed in the Kafka event body from the Dapr runtime. This one might look more familiar if you've done programming on Azure, because this is Azure Functions runtime. Azure Functions runtime is also portable. So we've taken Azure Functions runtime and put it on top of Dapr. And now we're going to take advantage of Kafka binding and logic apps output binding for Dapr to run Azure Functions on a Kubernetes, or actually right here on my local machine, and get both the benefits of Dapr, but the programming model and the tooling that would come with Azure Functions. And then finally, you don't need an SDK to use the event-driven functions as a service model. This is JavaScript, raw JavaScript here, that's doing the same thing. It's registered for a Kafka trigger with the Dapr, and it's going to be calling into logic apps the same way as the other ones. And let's launch them all. And then over here, I've got a little command line that's going to run a Dapr little Dapr app that's going to call into Kafka, put a message, and we can put in whatever you want. So anybody have a message that we want to tweet? What? Go Chiefs? No. You've just answered the question. All right, so this is dumping an event into Kafka, and you're going to see all of these pick it up through Dapr and trigger the logic app. And here's the, and there we go. Go Hawks from Dapr, from Lambda, and from functions. All right, so one last section here, topic, and that's actor model, which I also mentioned is like object-oriented distributed programming. Really easy for certain kinds of apps to map into, where they've got objects that encapsulate some state. A great example of this would be games. So Halo Online, if you've ever played that, you're working on top of the Orleans actor model, because in Halo Online, every game, every player, every high score, every object that's being tracked in Halo Online is implemented as an actor, a virtual actor on Orleans actor model. The challenge with Orleans is that it's .NET only. There's no support for any other language. So that's an example of being locked into, yeah, I really like that, but I'm now locked into that language only. But with Dapr, you get all of the benefits, all of these capabilities that come with virtual actors in a language-neutral way, if you want. Now, that doesn't stop you from building nice SDKs on top to make it easier to integrate with the language. But it means that I could write virtual actors in Rust if I wanted to on top of Dapr. So let's go take a look. And so the thing is with Dapr, too, and virtual actors, it takes care of, I mentioned, taking care of all distributed aspects, including resiliency. You can see if this node fails, the Dapr runtime, just like the Orleans runtime, just like Service Fabric Reliable Actors, would say, hey, I need to move all these actors from this node to a healthy one, and it's going to do that behind the scenes. The developer doesn't have to worry about it. The platform's taking care of it. And so that's built into Dapr as well. And so Dapr, for functions, worries about serialization, concurrency control, and activation. So if I reference an actor, Dapr creates it on demand. So again, really easy. If I want to create an actor with a name there that you can see, actor C, I just call actor C update, and actor C gets created on the fly by the runtime. Developer didn't have to go like pre-create these things, doesn't have to worry about shutting them down, like I mentioned. All of that's just handled for them. So let's take a look at a shock and awe demo. And I call this shock and awe demo because I want to show you that Dapr is not just a toy. It's meant for not just your simple 3 microservice enterprise LOB, but made for mission-critical Halo Online type scenarios. In fact, we're looking closely at Orleans performance characteristics and making sure Dapr matches it. But one of the ways that you can kind of see is how it does is how does it scale up? When I am creating hundreds of thousands of actors, how long does that take? So I've got this cloud-native parking garage app that I'm going to show you. Here's the scenario. Microsoft is growing to 1 million employees. And so we need a parking garage that supports 1 million spaces for parking garages. We got divided into 2 garages. Each one holds 500,000. You know what? We're going to just for A/B testing, we're going to do one of the parking garages we're going to monitor with actors written in Java, the other one with actors written in C#. And we're going to create 500,000 parking spots. And then we want to have Azure spheres in every one of those spots. And when a car comes in or leaves, it fires an event into the app that records whether the spot's in use or not. That's the app that I'm going to show you right now. And this is the last app. And we're going to time how long it takes to get to 1 million actors that have this state of parking app. So here's the .NET interface definition. Has car, get and setter. Here's the implementation. .NET parking garage, save data, which calls into save async, which is built on top of Dapr. And here's the It's initialization, initializes to false. Here's park, which says it to true. And get data to return the state of that slot. Here's the same thing, just in Java. Park and init. Here's the Java implementation. This is on top of the Java actor SDK for Dapr. And then I've got an example here, which is, I'm deploying this thing through Ohm onto Kubernetes into AKS. And so this is the Ohm manifest for the .NET actors, and then I've got the Ohm manifest for the Java actors. I'm going to go ahead and deploy this. Then I've got a Sphere device. I'm going to be also, the Sphere is going to be talking to Azure through Dapper to event hubs. So when I click a button on a Sphere up here, and the Sphere is going to fire the event into event hubs, which is going to cause those parking spots to fill up, 10,000 of them. And then here's the garage application all up, which includes everything. So if I go to, oh, I meant to start the timer. And the way that we can watch the status of this is one of the really cool things about Dapr 2. The back-end state store, that is sitting inside of Redis. And so what I can do is query the back-end directly. I don't have to go through the actors to get the state of all the parking spots. All I have to do is query the back-end Redis database, and I can wire that up into Power BI. And when I look in Power BI, this will show me the number of actors that I've got and their states, whether they're parked or not. And then one thing we'll do while that's refreshing is I'm going to show you the Dapr dashboard, which is a new project that also gives you insight into what's going on. I'm going to port forward it here. And then here's the Dapr dashboard. Here's the Redis database. Oh, and here you can see this is refreshing every 5 seconds. So I'm up to 610,000 actors on 20 nodes. If I do Kubernetes, I'll see all of the .NET and Java pods underneath that. And let's see where we are. So this is lagging a little behind. I've got 506,000 total. This is going to take another 10 or 15 seconds. While this is wrapping up, and I'll come back to it because we're a little bit over time, I know, let me just come back and give you a state of things here. Now, the community, if you want to join it, you want customers to join it, you want to partner with us, customers partner with us, let us know. You can see the kind of health of the community. 53 contributors, 25 components have been added to Dapr since the launch. We've got a little bit less momentum on OMP, but we're building that up. And here's a little bit of the roadmap. Where are we going with this? Building the open source ecosystem momentum here. And that is informing how we bring this out in Azure. The question that you'll say is, what about managed service? What's going on with managed OMP service? What's going on with managed Dapr service? The plans are still in development. But if we continue to have this kind of success, it has this proof of evidence that we're getting with our partners that we're working with, we're going to definitely be launching these things as services in the very near future. So that's kind of a little bit, I hope, give you an idea of where we're going. So the answer to the question that I got when I was walking in and said, hey, what's the deal with Service Fabric, Kubernetes? What are we picking on, betting on? We're betting on enterprise devs and enterprise dev platforms. That stuff's infrastructure. We're working on programming models for cloud-native devs to empower enterprise devs to be incredibly productive, like you saw. I think the calculator app is my favorite highlight of just how productive you can be on top of Dapr. And describe that app with Ohm, and then deploy it to AKS, EKS, or Raspberry Pi on-prem. That's the vision, cloud and edge, cloud-native programming for enterprise devs with us working with the open source ecosystem. So with that, let me go take a look, just one last thing, see how our scale did. Do a refresh here. Go take a look in the portal. We're at 868,000. So it's a little bit slower than it was this morning. But this morning, demo gods were friendly, and I was getting to 1 million actors in 1 minute. But that shows you these are a million concrete actors recording these parking spot controls. And so by any scale standards for a virtual actor framework, this is extreme scale, delivered in part because Dapr is intended to be extremely lightweight. So with that, I hope you found this interesting, give you a little view of where we're going. I want you to be part of it. If you're at all in this space, please join us up, join with us, share with your customers. And thank you very much. And I'll see you hopefully tomorrow at the data center talk. So have a great day.